should spend some time reading right at the beginning of Griffiths, his section 1.2 on the statistical interpretation. Okay, so spend some time and I'll talk about some of the things he talks about there. But the statistical interpretation. Of psi. And again, psi is the wave function or the matter wave or the probability amplitude. You'll hear all three names for those. Okay. Where does, in the arguments that I've been leading up to here, where does the statistical interpretation stem from? What argument have I used?
Probability density.
Okay, probability density from what? I started out with
E squared.
Okay, I start out with Maxwell's equations, right? And we put light through a double slit. And we solved Maxwell's equation, we got plane waves, and then through the double slit, on the other side of the double slit, we read an intensity pattern. The intensity is proportional to the energy, right?
Right.
The energy is proportional to the
Wave.
Okay, the wave, whatever the wave was, if it's the electric field, it was the electric field squared, right? We then went down to the one particle limit of light by turning up the attenuator, right? And when we got down to the one particle limit, we still saw that interference pattern. And so the best we could do about predicting where those particles of light would come out was a probability. And that probability was most definitely related to the intensity. And the intensity related to the energy, which was related to the wave function squared. Right? So this is all the connections that you guys should make. I'm not going to draw it again. I'm drawing it twice. Right? But the statistical interpretation that we built from that was that the integral from minus infinity to plus infinity of the wave function squared dx had to equal
1.
It had to equal 1. Alright. Now, one thing that we should talk about is that it's possible that the wave function could be complex. Alright? It's possible. Alright? The complex number comes in the following way. That if we're dealing with waves, do waves have phases with respect to each other?
Yes.
Okay, so if you have one wave and it starts off like a sine here, and the other one that starts out a little different place, there's a little bit of a phase involved with respect to those. You can incorporate that phase angle into the description between two waves with a complex number.
Right.
Right?
For the Euler relation.
By the Euler relationship, okay? So these could be complex. So what indeed is the magnitude of a complex number? Alright, what indeed is the magnitude of, how do you create the magnitude of a complex number? You got to use the complex conjugate. Alright? So what this truly is the integral from minus infinity to plus infinity of psi star psi dx equals 1. Where psi star means take the complex conjugate. What is it, just to review, what does it mean to take the complex conjugate of a complex number?
You just flip the sign on the...
Excuse me for 1 second, guys. Hello? Yes? Yeah, very little class. No big deal. What's that?
So you can change the sign on the complex part.
Yeah, you just change the sign on the I part and then
Yeah, okay.
multiply them or add them.
Yeah, change the sign on the imaginary part of the number.
Yeah,
And you multiply them, I guess.
I think so. Yeah, because
That looks like multiplying to me.
multiply them together.
Yeah, so if it's like, x plus 2i multiplied by
X minus 2i.
minus 2i.
Yeah.
Yeah.
You only ever change the complex part, though.
Yes, right.
Unlike with a regular conjugate, which you change whatever you feel like.
Cancel each other up, and
Correct.
I becomes a positive.
Yeah, it's just like factoring x plus x minus 4, and then it's like x plus 4, x minus 4, middle term cancels right.
Yeah.
It's the same thing, you just gotta think I.
Yeah, I'm not going to be into my So this is statistical interpretation of quantum mechanics. All right, great. So what did we discover this as? The units of this thing?
Probability per unit length.
That's probability per unit length, okay. And in general, the wave function is going to be the probability per unit space that you solve the wave function. Right now, we've just done one-dimensional. But if I solve for like a hydrogen atom, where the probability density is not just one dimension x, it's r, theta, and phi, spherical coordinates.
Right.
So what would the probability, what would psi square psi, the units of that be? It would be probability per unit volume, okay? And in that case, you would want to integrate, it would be a triple integral over some volume of either psi star psi dy.
The complex conjugate, which is is an inverted matrix.
So a complex conjugate of a complex number is simply, if I give you a complex number, a plus ib, the complex number is wherever the complex number is, you make it the opposite sign. So the complex conjugate would be a minus ib.
Right.
If I gave you a minus ib and asked for the complex conjugate, it would be a plus ib. Okay? Okay. Yeah, so before we get fully into the probability, here's what we're led to conclude, and this is what Griffiths takes over, is this interpretation kind of gives us something like this. Here's psi. We'll do psi of x at some t, given some t, for a given t. Psi at some t. So I only have to plot it versus x over here. If we have a wave function that looks like this, the probabilistic interpretation, by the way, the statistical interpretation was explained by Born, Max Born, and that's the guy who's Olivia Newton-John's granddad, that worked with Pascal Jordan, and that article, and got very complicated. They wanted to give him the Nobel Prize and everything.
They worked with a Nazi. So.
Yeah, so that was Pascal Jordan, yeah. So ultimately the Nobel Prize, I think, was given in 1954 to the statistical interpretation of the quantum mechanics, because that was just born, right? But the statistical interpretation goes like this. So let me do better. Let me do this is really psi star psi of x and t. Okay, so it's not just the wave function, it's the wave function squared. Alright? So as soon, what we're going to do now is this is before measurement. And then after measure. So if we go and we measure something, we say, okay, here's some particle, we just solved for an electron. We just solved for an electron in some funky potential. So here's x equals 0, here's x equals L, x equals 0, here's x equals L, and there's some
potential energy or potential voltage.
It's a potential energy. So a voltage is not an energy. Okay, so you've got to make it into an energy, which you usually have to multiply the charge times the voltage. Okay? So it's a potential energy. And we solve for the wave function, and then we plot the wave function squared, and we come up with some curve like this. What this interpretation, Born's interpretation is that before we make the measurement, where is our electron?
Anywhere in there.
Somewhere in there.
Okay, it's somewhere in there.
Probability that's halfway between.
Okay, the probability is highest that it's right there. Alright, so that's one question that we could ask. Alright, but what we also say, and this is the funkiest part of quantum mechanics that doesn't have a great answer. Alright, and it's called the Copenhagen interpretation of quantum mechanics.
Would be the orthodox view.
Okay, yeah. As soon as we make a measurement, and if we find from that measurement that the particle's right there, right? Then what happens is, after the measurement, let's just say it turns out to be right there, x7. Then indeed what happens is that wave function completely collapses onto x7. So this would be psi x comma t2. So this is at some other time. Psi of x comma t2. All right, so what's happened is, as soon as we make a measurement, we collapse it here. All right, and so this is where everything gets kind of interesting philosophically, and this is where Griffith spends some time. And what Griffith talks about are 3 points of view, all right, on this whole quantum mechanics business. All right, and the first one is this realist position. And this is kind of a position Einstein really liked. And what happened is the following. In the realist position is, they said, look, it's an electron. It really wasn't everywhere. Right? It really wasn't everywhere before you measured it. It really was at x equals 7. Right? But the problem with quantum mechanics is that there are some variables that we don't know. There's some physics that we don't know. The particle it's carrying some additional variables. And if we had a better handle on that, then we'd lose this whole picture probably. And we would know for sure that the electron never was.
That's a sensible thought.
It's very sensible. That's why it's called the realist. That's why Griffith said it's the realist. Let's make it more absurd. Let's make it an elephant. The elephant's in somewhere between here and here. Where is it before we measure the elephant? What quantum mechanics is now telling us is that the elephant is everywhere. That the elephant's wave function is everywhere. Right? And that has some issues with a lot of people. Realists wouldn't like that. And say, look, there's a hidden variable on the elephant, that if we had control on that, we wouldn't have this discrepancy or this unknown.
Right.
And so, what Einstein and a realist would say is that we're missing something. The quantum mechanics is great, but it's kind of missing something. It's missing some hidden stuff that we just don't know about. All right. But then there's the orthodox view, and the orthodox view is, no, this is the way it is. All right. We may not like it, but this is the way it is. All right.
They don't ask questions.
And then and there's like
then there's the
I want to say the atheist view, but the agnostic view.
The
All right, the agnostic view is, why even ask? Just shut up and calculate.
Yeah.
All right? It works great, just shut up and calculate, it doesn't matter. All right? And it's very great to think about these things, and great physicists continue to think about these things. All right? But what's important, I want you guys to now do, is if you read that section of the book, you'll then skip to chapter 12. I want you to read chapter 12 over the weekend.
Really?
Yeah, fine. Okay, and over the weekend, read chapter 12. And in chapter 12, they're going to talk about, Griffith talks about 3 experiments. It's Einstein's EPR experiments on the spooky action, and then further was Bell's inequality, which dealt with hidden variables. All right. Then there's the quantum Zeno's paradox.
we learned that in calculus.
Yeah, there's a couple other experiments. But in any case, chapter 12 is about the following: that it's not a question of metaphysics anymore, which view is correct. The hidden variable or the orthodox view or the agnostic view. That somehow, and in particular John Bell, was able to show that there's a physical difference that can be measured between, in particular, the realist view and the orthodox view. Because if you think about how hard this is. You go to measure an elephant, and the elephant's right here, right? That's not the question. The question is, where was the elephant right before you did the experiment?
Yeah. Well, they're saying that the elephant came into being at that position through the act of observation.
Yeah, it's very funky that it came into being. I don't know, all right? So it's a very hard question, and it was a question that Einstein, Podolsky, and Rosen kind of really set up in 1935, and they set it up as a contradiction, that this interpretation led to a contradiction between entangled pairs.